Hi, my name is Brad, and together with my supervisor Kamal, we've been looking into gradient descent algorithms for local Nash equilibria in differentiable games. So we'll start off with a little bit of background knowledge. Firstly, what is a bimatrix game? So a bimatrix game, by definition, is just a two-player game represented by two different matrices, and where the playoff strategies and payoffs are captured by these matrices. Each player in these games has a finite set of strategies in which they can choose from, and their payoff matrices can be combined into this sort of bottom form here, in which you have the row player and their payoffs in the bottom quadrant, column player and their payoffs in the top quadrant, and then their probability of choosing either move A or move B, represented by x1 and x2. Next, we have the Nash equilibrium. And what this is just a situation in a game where no player can benefit from a unilateral change of strategy. And so what that really means is that both the players are in a mutually agreed best response, and they don't really have any incentive to deviate from their chosen strategy. So there's a few different types of Nash equilibria, mainly the pure strategy and mixed strategy. Here a pure strategy will just be where a player chooses one strategy consistently, and a mixed strategy is when they have a probability defined as p of choosing a certain strategy and minus p for the opposite. 1 minus p for the opposite. And it is just worth noting that there is always guaranteed to be the existence of one to multiple different Nash equilibria in finite games. Next, we have gradient descent. So gradient descent is just a optimization algorithm that works by trying to minimize a cost function by iteratively updating its parameters. So the concept is really it's just trying to move towards the global minimum of a cost function by taking steps in the opposite direction of the slope at that point. And it's governed here by the update rule as below, and can be controlled by a learning rate parameter, which will affect its convergence speed and stability. So the motivation behind why we want to look into finding these Nash equilibria in games is currently in differentiable games this can be quite challenging. There are problems with the potential for cycles being formed with current algorithms, where the algorithm will cycle around the Nash equilibria without ever converging to it. They can also be rather slow to converge to these points and very complex. And if we are able to help solve some of these problems, it would have applications for things such as general adversarial networks and multi-agent reinforcement learning. So moving on to one of the first algorithms that we looked at, symplectic gradient adjustment. So what this is an algorithm that is designed to help address the limitations of traditional gradient-based methods in game theory, and it does this by trying to target the cyclical behavior and convergence issues of the differentiable games. And how it does this is it sort of draws inspiration from the symplectic integrators used in Hamiltonian systems in physics. And what this helps do is combat the rotational forces that can be seen in this antisymmetric component here, and then mitigate them. So unfortunately I won't be able to show it today, but there was a lot of math that was involved in trying to derive what the update rule for this algorithm would be, and then this was the final result of it. Main things to just note is this second part of the equation here, in which we have the antisymmetric component of the Jacobian multiplied by the gradient descent of the game. And so what that is doing is that is the part that is mitigating those cyclical components. Next, we move on to competitive gradient descent. So this is an algorithm in which you sort of try to take a very localized version of the game and then consider what the Nash equilibria is going to be at that point. This algorithm has actually taken inspiration from the Taylor series, where for a given function at a point you're trying to best estimate what the curve is. So it's doing a similar sort of thing. Here the update rule incorporates an interaction term between the two player strategies, and what that does is it allows the algorithm to consider for one player what the best move would be, taking into account that the second player is going to be choosing their most likely move. And once again, here is the derived update rules for this algorithm. Once again, the important part here is at the end, where you can see that for the row player here, they are taking into account what the column player's gradient is at every point, and this helps with the update. So moving on to some results now. To begin with, I just benchmarked it on a very simple zero-sum game here, so this is sort of no gain from any move or action taken, and that can be seen very clearly by the resulting graphs, in which the probability for choosing either action is 50%, so this was a mixed strategy equilibria, and that can be seen across the board for both algorithms with their different parameters. Moving on next to the prisoner's dilemma, which is a bit of a famous game. In this case here, it can be seen that the symplectic gradient adjustment was able to reach the Nash equilibria of the bottom quadrant here of 2, 2. This is the global minimal option for the game, but it is worthwhile noting that it is also unstable. And it was able to do this rather quick compared to competitive gradient descent for a high enough lambda, when lambda was above 0.5. But competitive gradient descent was still able to reach the other Nash equilibria here in relatively fast speeds. Lastly here, we just have a game that I designed myself called Mutual Agreement, in which the players here both really only benefit if they choose the same option, and just trying to see if we can test algorithms out a little bit. And it does look like the algorithms took a little bit longer to converge here. As you can see, the number of iterations required with a low enough lambda in symplectic gradient adjustment was around 1400, but eventually all the different players at their learning rates were able to converge to Nash equilibria. And for any parameter of lambda higher, it does look like symplectic gradient adjustment started to struggle. As you can see, all of player 1's decisions never reached a Nash equilibria and stayed at the middle point, which in this case wasn't a Nash equilibria. Competitive gradient descent did well here, and all players were able to reach a Nash equilibria in relatively fast speeds for the different learning rates. So that's good to see. So yeah, in summary, both algorithms performed rather well for just a few of the different test cases that were showcased here. Only one that seemed to have struggled was just the symplectic gradient descent on that last case, and sometimes the competitive gradient descent was a little bit slower than the symplectic gradient adjustment. Looking into future works, if I had a bit more time, I would like to extend my current derived methods to more sophisticated applications and start looking into maybe some models like the generative adversarial networks, just to see how they apply there, and also look into maybe developing a bit more of an adaptive learning rate technique that is able to dynamically adjust itself to have a higher learning rate when the convergence is being rather slow, and then reduce the learning rate as we narrow in on the Nash equilibria and having some convergence issues with cyclical oscillations. Alright, thank you.